Hello, everyone. Welcome back. This video is going to cover Chapter 10, which is about correlation and linear regression. We are going to start with correlation. Correlation to us is just going to mean that there's a connection between two variables, two concepts, two ideas. So a correlation exists between two variables when the values of one variable are somehow associated with the values of another variable. I want to make it clear, if we can find a linear correlation between two variables, that doesn't mean that one is necessarily causing the other one. It just means that there's a connection there. There's an association between the two. You can look up in philosophy the correlation versus causation. That's a whole thing. Moving on. Where there is a correlation and the plotted points of paired data, the graph can be approximated by a straight line called a linear correlation line. And here we have a few graphs, and this is going to kind of make the point for us, is if we have all this data, is there a straight line that can sort of represent the data to give us some predictive power, meaning that we can predict things? This is considered a positive correlation. If you remember back in your algebra class, y equals mx plus b, m being the slope, and you can see this slope has a positive slope. There's a positive correlation here versus this one next to it. Even though there's a stronger correlation, this definitely has a negative correlation, a negative slope, as it were, meaning a positive correlation. As x gets large, y is also getting large, versus a negative correlation, whereas x gets large, y is getting smaller. Now, these other two graphs are showing us that we do not have a correlation. In fact, this graph C here, there is no correlation of any kind. It's just a bunch of scattered, there's no one line or graph that could make it work. However, if we look at graph D, we can definitely see there's a correlation. It's just definitely not linear, meaning there isn't a straight line that's going to work. This one looks parabolic to me. Now, you'll notice underneath each of these, we have the letter R. Let's talk about what that is. The linear correlation coefficient R measures the strength of the linear correlation between the paired quantitative x and y values in a sample. Now, we use the letter R to represent a sample pair data. It's the linear correlation coefficient between the paired data versus the Greek letter rho. Now, I know it looks like a little p there, but it's actually a Greek letter rho. In fact, what we're going to be comparing with this is rho, we're going to assume is equal to 0 versus rho is not equal to 0. Now, rho is the population linear correlation coefficient. Rho is what we are actually testing against. And let's talk about some properties here. Here's the crazy formula for the sample linear correlation coefficient. This is the wildest formula in the entire course. However, the good news, once again, is that our calculators are going to be doing all of the heavy lifting. The test statistic is here. We have to calculate the R from the equation above, and that's divided by the square root of 1 minus R squared over n minus 2. I want to make it clear, our degrees of freedom is n minus 2 in this case because we have two sets of data. And we often just round the linear correlation coefficient off to 3 decimal places. And there's reasons for that. Back when we used to use tables and things, they usually rounded them off to 3 decimal places. Let's talk about some properties. R, the linear correlation coefficient for the sample, is always going to be between -1 and 1. And the closer to 1 or -1, the stronger the linear relationship. The closer to 0 is the weaker the relationship. And I want to go back up to these graphs up here real quick. And you can see A and B are very close to 1 and -1. In fact, you can see B is very close to -1. However, when there's no correlation, R is at 0. And when we have a nonlinear relationship, it's also, excuse me, closer to 0. Again, I want to point out my null and alternative hypothesis. We're going to assume that the population linear correlation coefficient is 0. In other words, we're going to assume there is no linear correlation. no correlation. Opposed to our alternative hypothesis, where we think that there is a linear correlation. And we'll come back to that. All right, so here is, excuse me, a problem from ALEKS. We can see our figure 1 doesn't look like there's any kind of a correlation at all. Figure 2, it looks like there's a somewhat of a linear correlation with a positive correlation, positive slope, versus figure 3, where we have a loose linear correlation, but we definitely have a negative correlation, versus 4, where that looks like a perfect 1. That's like a perfect linear correlation. So let's see what we're going to be asked. Which set of data has an apparent negative but not perfect linear relationship? That is definitely going to be figure 3 for us. Part B, for which data is the sample correlation coefficient equal to 1? That is definitely this one here. I mean, we have a perfect straight line. So that's going to be figure 4. For which set of data is the sample correlation coefficient closest to 0? I'm going to call it figure 1. That one looks like there's no linear correlation of any kind. So I'm going to call figure 1. Which data set indicates the strongest positive linear relationship between its two variables? That's again going to be figure 4. That has that perfect straight line there. All right, that is correlation. Excuse me, let's talk about regression, specifically linear regression. There are lots of regression models out there. So this is going to be linear regression. Given a collection of paired sample data, the regression line is the straight line of best fit for the scatter plot of the data. And the regression line is going to be in this form here. Now, you might be thinking, I remember my straight lines look like this. And that's true when we're in an algebra class. In a stat class, we use the regression equation. A is going to be B in our old equation, and B in our new equation is going to be our M, our slope. And let's get some definitions out of the way here. X is called the predictor. Variable. Y is called the response. A, in this case, is the y-intercept. And B is the slope. All right. Let's go to our first example. Interpreting the slope of the least squares regression line. That's what the y hat equals a plus bx. The Cadet is a popular model of sport utility vehicle known for its relatively high resale value. The bivariate data given below were taken from a sample of 15 cadets, each bought new 2 years ago, and each sold used within the past month. For each cadet in the sample, we have listed both the mileage X in thousands of miles that the cadet had on its odometer at the time it was sold used, and the price Y at which the cadet was sold used. Now, they give us our least squared or linear regression equation. And we can see the line. Can you see that the slope is negative there? And we can see that the slope here is negative 0.5. And we have this data. And what we are going to be using in this case is that linear regression equation. I'm going to rewrite it down here. And part A says, for these data, mileage that are greater than the mean of the mileages tend to be paired with used selling prices that are below the mean of the used selling prices. That means that that we have a negative slope. So the further to the right we go in the X direction, the lower the price is going to be. is what that's saying there. And according to the regression equation, for an increase of 1,000 miles in cadet mileage, there's a corresponding decrease of how many thousands of dollars in the selling price. And that is a little tricky. That is the 0.5. And I'm putting a positive 0.5, even though it's negative, because they specifically tell us that it's a decrease. So how much is the decrease? It's a decrease by 0.5. So be real careful with the sign there, SIGN, as you're looking at that. All right, let's get some data out of this. A financial analyst is examining the relationship between stock prices and earnings per year. She uses 15 different traded companies at random and records for each of the company's current stock price and the company's earning per share reported in the last 12 months. Her data are given below, with X denoting the earnings per share from the previous year and Y denoting the current stock price. They're both in dollars. Based on these data, she computes the least squares regression line to be, and we once again have our least squares regression line. Based on the analyst's data and regression line, answer the following. From the regression equation, what is the predicted current stock price in dollars when earnings per share is $55.96? And we're going to round to 2 decimal places. So this is going to be Y hat. Oops. Y hat is equal to negative 0.001 plus 0.039 times 55 times 96. Let's see what we get. So negative 0.001 plus 0.039 times 55.96. So it's about $2.18. And that is our actual answer there. And from the regression equation, what is the predicted current stock price in dollars when the earnings per share are $19.67? Well, we're going to do the exact same thing. I'm going to go Y hat equals negative 0.001 plus 0.039, and now it's 19.67. Let's see what we get. Negative 0.001 plus 0.039 times 19.67. It's about 77 cents, looks like. Not too bad. All right, now let's do a full-on hypothesis test. And we're going to start with forest fires and acres burned. An environmentalist wants to determine the relationships between the numbers in thousands of forest fires over the year and the number in hundreds of thousands of acres burned. The data for 7 years are shown. So we're going to start here with our null hypothesis, which again is going to be rho, which again is population linear correlation coefficient. We're going to assume a 0, which means no correlation, versus rho not equal to 0, which means we think that there's some relationship, so a correlation. So first we're going to select the graph. I'm going to show you how to do the graph with your graphing calculator. I'm going to go second, and then right above it is the y equals. And I'm going to turn on my plot. And the type is going to be a scatter plot. The mark that I'm going to use is there. And actually, my data, I want to show you, is not in list 1 and 2. It's in 5 and 6. And I'll show that to you in just a moment. So I'll quit out of that. And let me show you my data. You can see the 72, the 69, and so on. So I'm now going to graph this. At the top right, it says graph. I'm going to hit that. And nothing shows up. So what I need to do is I need to go to zoom. And I'm going to scroll down until I find zoom stat. And now I can see my data. And let's compare this data here to our graphs. And it's looking to me like it is D. Now, notice it's not exact, but D is definitely the closest one here to our scatter plot. So I'll quit out of that. All right, so we're going to compute the correlation coefficient and test its significance at 0.05. I want to point out another way that we could do this graphing is I could look at the data and find 72, 62, and I'm going to find that point. So 72 is about here. 62 is about here. So there's my point. And you'll notice at 72, 62, maybe there's one there, not really one here. And so that's the other way. In fact, when we do the other example, I'm not going to use the scatter plot at all to predict that. Okay, so we are going to use to find the correlation coefficient, we're going to use linear regression t-test. And mine are again in list 5 and 6. So stat tests, and it's way down towards the bottom. Linear regression t-test, there it is. And again, I'll have to change mine. L5, clear L6. And we're going to calculate. And you can see R right there. R is about 0.7708. And they want us to give a p-value. Now, it very nicely gives us the p-value right there. That's 0.04249. And our alpha is given as the 0.05 that is right here. I can see right away that that is just barely less than 0.05, which means for us that there is a significant linear relationship between the number of forest fires and the number of acres burned. Not too bad. Let's go on to our last one. NHL assists and total points. A random sample of scoring leaders from the NHL showed the following numbers of assists and total points. And they want to know, is there a significant relationship between the two? So let's start here. Row is 0, or row is not equal to 0. We're going to pick our graph, and I told you we were going to do this one a little bit differently. So I'm going to go to 65. Let's do this. 65 is right here. We're at 86, which is way over here. And I can see there's nothing there. So it's definitely not A. It's not B, or it's not C or D. But we can see 65 and 86 over here. We definitely have something there. So B is going to be my only possible answer as far as the graph goes. You can put the numbers into a graphing calculator and plot them as well. That's another option. I just wanted to show you that we can do it even without that. All right, we're going to compute R. I'm going to use a slightly different calculator for this one. So we're going to go stat, we're going to go to tests, and I'm going to go down to linear regression t-test again. And I can see that R is 0.83487. So R is 0.835, we'll say. The p-value is over here at 0.194. .0194. Now we are comparing that to our alpha, which is right here. And I can see right away that that is just under my 0.02. So we're going to reject the null hypothesis. I don't think I put reject on the previous problem. Yeah, we're going to so go back, reject. And that tells us that we are in support of the alternative hypothesis, meaning that there is a linear relationship between the assists and total points. I hope that you found that useful.